Muy buenos días a todos ustedes. El Planetario Luis Enrique Erro y el Instituto Politécnico Nacional tienen el gusto de recibirlos en este segundo día del cuarto Festival Internacional de Planetarios. En esta ocasión tenemos con nosotros la conferencia de SubbaRao. Él es director del Laboratorio de Visualización Espacial del Planetario Adler de Chicago. Es doctor en astronomía y director del Laboratorio de Visualización Espacial en el Planetario Adler de Chicago. Su área de investigación es la cosmología, particularmente la estructura a gran escala del universo. Fue constructor de la Sloan Digital Sky Survey, proyecto que desarrolló un mapa 3D de más de 1 millón de galaxias. Desde hace algunos años, Mark utiliza las capacidades de los teatros inmersivos del Planetario Adler en su trabajo científico de la visualización. Actualmente preside el grupo de trabajo de visualización de ciencia y datos de la Sociedad Internacional de Planetarios. Él es también el creador de las proyecciones a domo completo para Planetario Digital, Planet 9, Cosmic Wonder y Welcome to the Universe. Recibamos con un fuerte aplauso a SubbaRao.
Thank you very much. It's a real honor to have the opportunity to speak to you, and it's also a real honor to get to talk in this beautiful planetarium. So this is really a wonderful conference, and I'm glad to be able to come back to it. So if you could go to the next slide. What I'd like to talk to you today is about what's been happening in scientific visualization in the planetarium, and particularly what we've been doing with the International Planetarium Society to help advance that. 2 years ago in Cozumel, I spoke about something called the Data to Dome initiative. We were just starting then, but we've made a lot of progress, and I'd like to report to you on some of that progress. The idea behind this initiative is that these facilities that we've built have incredible power. They have much more power to do many more things than the tools we had in the past. But with great power comes great responsibility and also great opportunity. And challenges. How do we deal with all of this? So one of the things we've been trying to do is really take the ways that we work and move them closer to the way that scientific data and information and discoveries are produced, to make that whole pipeline of something being discovered or some beautiful image being taken to it showing up in our dome quicker, so we can be more immediate and improve the sort of urgency and the quality of scientific communication around the world. Next slide, please. So last March, we held this workshop in Japan. It was an incredibly successful workshop. We had 50 or so attendees, most from Japan, but attendees from around the world as well. And we also had many people watching online where these videos were live streamed. We have a little bit of problem with the slides, but I'll hold on. And what I'd like to do is actually take you through some of the items that were discussed there. We set this workshop with a pretty big goal, and that goal was to advance the state-of-the-art in big data visualization in the planetarium. This is with an acknowledgement that there are projects coming up that are going to produce data sets and information in quantities that we haven't dealt with before, and we're going to have to think now intelligently about how we handle that. Well, this is probably my fault because they're using my computer, so I take full responsibility. see. Does not like that slide. Shall we try the next one? All right. Well, they're working hard there and coming up with a solution. So let me just I'll tell you a little bit about this workshop. So this is something we had been planning for a number of years since we started this Science and Data Visualization Task Force with the International Planetarium Society, and it's something that the kind of thing that I think IPS is going to start doing more and more as we try to develop or build an organization that is more active and more responsive to the needs of the community. It was held jointly between IPS and the National Astronomical Observatory of Japan, who provided some incredible resources. And the National Astronomical Observatory of Japan is an interesting place because they've actually built a planetarium at a research facility. And this is a really great model, and they're also investing a lot in scientific visualization. So we basically had a mixture of workshops, which we went through different techniques, some talks about interesting topics, and practicums. And these were working sessions where people would sit down with their laptop and practice the things that they learned in the workshop or were demonstrated to them. All right, what do we think? Is it going to stay? All right, I got my fingers crossed now. So, and thanks for your hard work there, getting this going. So that was the goal, a pretty lofty goal. We wanted to advance the state of the art in data visualization in the planetarium. Next slide, please. And there's the group of us. This planetarium is actually a 3D planetarium. Actually some pretty, I know people have mixed opinions about 3D in a planetarium. This is some of the best 3D I've seen in a planetarium anywhere. Next slide. I just thought this picture was funny. I had nothing to say about it, but I thought I would include, you see Ian McLennan there with his HTC Vive. Next slide. So like I said, we really want to deal with this issue of big data. So we had some people talking about the current big data projects in astronomy. So Satoshi Miyazaki is in charge of the Hyper Suprime Cam, which is one of the largest cameras in astronomy, which is mounted on the SubbaRao telescope on Mauna Kea. So this telescope, this camera produces incredible amounts of data, huge imaging data. Next slide. And we also had an opportunity to get hands-on with some of these big data sets ourselves. So this is something that you can go to the website, and there are tutorials and instructions for you to follow. There's a GitHub site, there are Python notebooks, and you can work through the process of downloading all of the Gaia data and building a texture map of where stars are in the sky. So this is Sunhiko Kato. If you go to the next slide, you will see an example of that. Really beautiful map. This first data release of Gaia is incomplete, but even with the incomplete data and missing bright stars, you still get a beautiful map of the galaxy. Next slide, please. Optical astronomy has some big projects like we just saw, but in radio astronomy, data sets can get really huge. And that's because you're not just dealing with two-dimensional images, but you often have three-dimensional images. So you have multiple channels of velocity space. And that can make for real challenges in both visualization and interpretation. If you go to the next slide, we saw some nice examples of how to deal with that data in the ALMA project. And these are online tools. There's really been a revolution in what can be done inside the browser with web tools. And so these tools allow you on the server to take what are these huge data cubes, examine a portion of them, visualize that in your browser, and then only pull back for analysis the part of the data that you want. Because it turns out most of that data you're often not interested in. So you see some examples here. Next slide, please. So that's the current generation of, sort of represents the current generation of big data astronomy projects, but the next generation is coming. So we heard some talks about that. Ben Emons gave a talk on the Large Synoptic Survey Telescope. Next slide. And that project is progressing very well. You can actually see the facility being constructed in Chile. You can go online and watch that on a webcam every day. And when this project goes online, the quantity of data that will come out will be incredible. We will, for example, discover tens of thousands of things every day that have changed on the sky. And we want to be able to do things like stream that directly into your planetarium. So you could say, last night, these supernovae were discovered. This many asteroids on a daily basis. You saw there some of the data sizes. So we're talking about exabytes. A lot. Next slide. So then the topic is, how do we deal with this kind of big data, and how do we visualize it in the planetarium? One area where we've been dealing, these sort of observational projects are really expanding their data sizes, but one area we've been dealing with that for a long time is in computational astronomy, where we can produce in our computers as much data as we want, really as much as we can store. And so here's some examples of techniques used to visualize really large particle simulations. If you go to the next slide, we'll see a particular example that we saw a demo of, which is dealing with the formation of interesting structures in Saturn's rings. And these are gravitational simulations with lots of particles and the formation of these little propeller structures. So if we could bring down the PowerPoint and play the first video clip, we'll watch a dome version of this visualization. So if you saw in the previous slide, at times there are 6 billion particles entering into this simulation. And a mix of techniques are used so that nearby we're actually rendering little tiny spheres. But as we get farther away, we move to just rendering little flat planes that have the image of a sphere, but are calculating in real time where the lighting should make that appear. And you can't really see the difference as we switch between the spheres nearby and the billboards further out. So this simulation is trying to show how these strange propeller structures form, something that we've seen in the Cassini imaging. There are a lot of them. Another technique that's used is the simulation is only over a relatively small area, but it's reproduced and blended together to seem like it's going off into infinity very effectively. So here we can see, what a smaller region of that simulation volume looks like and see what is happening to create these propeller structures. We believe they are formed by things called moonlets. So an object bigger than a ring particle, but smaller than a moon, smaller than a shepherd moon. There you see that blending to create sort of the infinite field, how effective it is. Great. So next slide, please. Another one of the talks that I found particularly interesting was this one from one of the other visualization experts at NAOJ about using the game engine Unity for data visualization. In particular, as we start to expand and create things not only for the dome but for VR as well, it's nice to have a way of working that works well in both VR and in the planetarium. So this is a very promising avenue. Next slide. So Unity is a game engine, right? It makes video games for everything from your phone to like high-end commercial video games. It's a very powerful tool. Next slide. And we saw an example of a pretty incredible visualization that was created with Unity of flying through the 3D structure of our galaxy. I, however, could not find a dome version of that. I'm not sure if version's been rendered yet. So I'm going to show you another visualization that was done by the same person, Hirotaka Nakayama. So if let's bring down the slides and show the giant impact. So this simulation represents the impact of 2 protoplanets early in the solar system, something that likely happened quite frequently. With 2 Mars-sized bodies. This is similar to the kind of impact that would have created the moon, but in this case, we have 2 equal-sized bodies with the collision. Again, this is a similar technique in that we have a particle simulation, lots of particles, and we're rendering out those particles in a way to create a volumetric effect. Yes, it's a really beautiful simulation. Thanks. And if we could go to the next slide. They're the credits for this visualization. Next slide. As part of the online resources for this workshop are full instructions on how to do a data visualization in Unity. And this really is, I've searched the web, and this is by far the best example of this that's out there. So if you're interested in doing some sort of scientific visualization using the game engine Unity, which you can do with the free version, I encourage you to check that out. So this is the example that we run through of how to take a table of data, in this case it's chemistry data, and produce something that you can visualize in this game engine. You can immediately get it working in VR, and through some of the further instructions that are in this tutorial, you can render out a movie for Planetarium. Next slide. And this goes through some of that process, and what is laid out in this tutorial is actually how to visualize the data using something called programmable graphics shaders. And this is something I'll come to later in my presentation. But this is a really powerful way to programmatically control in a very performant way how things are visualized in real-time computer graphics. Next slide, please. And then the tutorial also works through some more advanced lighting effects. In this case, you're seeing what's called fog, where you get a sense of depth perception by, and this is the kind of thing you can do with programmable graphics shaders. You can say, if a particle is farther away, I'll make it bluer, and that's a fog effect. Next slide. So that's on the science and the visualization side, but a really important development that's been happening in the field has to do with how we distribute this content once it's made to the planetarium community. And in particular, this project, Data 2 Dome, with the letter number 2, it's a new format for scientific agencies, or really anybody who produces content, to put their information on the web in a way that it can be registered, so planetariums around the world can sign up for that, see the information as soon as it comes in. So this is how we're going to bring content directly into the planetarium very, very fast. Next slide. And this this flow chart shows what that process looks like. You have content providers. We're also working very closely with the planetarium vendors so that we integrate into their cloud systems. And they register this Data to Dome content. And the planetarium can go through their GUI, see what's available, download it, and project it directly into their dome. So to give you an example, if we go to the next slide, we'll see how that's implemented in the Digistar 6 system. So here is my control interface, and we in the library there is Data to Dome content there, and right now there's a service from ESO and ESA. And in that, you can see what's available. Their images, their full dome images, their spherical images, there's videos. And I can select them, I can read about them in the interface, and then if I want it, I can click the download button and download it to my system and display it right away. So what that means is, as soon as a new image is taken, and as soon as this content is released in a press release, at that moment, it's available to you in your system. So this is the state of the project now. We're continuing to expand it. More and more vendors are signing on. Evans and Sutherland was the first. And also, we're looking at ways to have more and more different types of data integrated into the standard. So pay attention. Next slide. I mentioned before the practicum session. So this was a really nice opportunity to sit and work together as teams. So here's one picture of that. Next slide. And one of the things that I'd like to show you is something that we actually made during one of these practicum sessions. So we have a little video, which is the gamma ray burst video. If you could start that now. So this was a section from my practicum session. What we did is we, as a group, we built a Python notebook, which accessed a database online, downloaded the data from Fermi gamma ray burst, and we imported that into Worldwide Telescope, created a little animation, and rendered it out. So if we could bring down the slides and play the GRB movie. So all this from accessing the data to rendering the movie was done within that little practicum session. So here is the Fermi 3-year gamma ray map, and as we run time forward, we'll watch these gamma ray bursts go off like popcorn across the sky. Of course, one of the big discoveries was that these did not seem to be aligned with the galaxy at all, but were occurring all throughout the sky equally, which led to the realization that these were coming from cosmological distances and must be incredibly powerful events. Next slide. Hopefully you all got a chance to see this article. It was actually listed under the resources at the on the website for this conference, and it was mentioned yesterday during the opening ceremony. But this article by Tom Kwasniewska in Nature, or this column really, I think it's a very important thing for our field. It's something that we've been working for a long time, and what it really is it's an invitation to the scientific community, the world scientific community, to come in and use the planetarium as a visualization facility. And that's an invitation that we all have to respond to. So hopefully people are reading this, and it will encourage people to be more interested in what's happening in the planetarium. There are a couple of things here that you see. I mean, one is the argument that most scientists are vastly unaware of the power of these facilities. And they have no idea that they could really be used to advance scientific research. And you see that in bold. Planetariums are, for the first time, able to give back to the scientific world. So this idea that we can do more than just public outreach, that maybe in off hours or at various times, we could actually be used by researchers to advance scientific knowledge by using the planetarium as a data exploration, investigation, and discovery tool. Next slide. One of the things that was mentioned in that article was the new planetarium in Cape Town, the Zico Planetarium, and Digital Dome. I was there 2 weeks ago for the opening, and this is a really unique facility. what makes it unique is how it was funded. It was funded through a partnership between the museum and a consortium of local universities led by the University of Cape Town, with the idea that it would be a dual-use facility. Sometimes it's used for planetarium shows and public showings, but sometimes it's also reserved for researchers to explore their data. So if we go to the next slide, on the right you'll see one of the astronomers, Tom Jarrett, and myself at the opening, where we had a competition for who had the most ridiculous tie. And so the question was, who won? Tom said it was a tie, but it's a bad joke. And there you see on the left, Tom in the planetarium looking at one of his data sets. This is a galaxy survey that he's worked on for many years. It's a beautiful planetarium, actually very, very similar in technology to the planetarium here. Next slide. One of the other points that's made in that article is that it doesn't have to just be astronomy anymore. We've seen that with some of the stuff we've seen today. Sean mentioned in his remarks the day before this Neurodome project, which was exploring brain structure in a planetarium. But it really could be any science. But I happen to have a clip of this one. So if we could bring down the slides and play the Neurodome clip. One of the things that makes neuroscience particularly interesting topic for planetarium visualization is the wealth of different imaging techniques and three-dimensional high-resolution imaging techniques. So the visualization of which can actually be quite challenging. Consulted on this, and there are challenges you have to deal with dealing with some of this data that we rarely have to face in astronomy. There are also a lot of similarities, one of which is the range of scales, physical scales. So you want to understand things on sort of the whole brain scale, like we're looking at now. You also want to understand things down on the neuron level. In fact, sort of interesting fact, the number of neurons in the human brain is almost exactly the same as the number of stars in the Milky Way galaxy. So this visualization was done all using real-time software. So this like high-resolution 3D scan of neurons was put into was visualized using a technique called splatting, where the brighter parts of the scan got little markers that blend together to show the shape of the neurons. And then we sort of fake this technique to show neuronal activity. This is perhaps the most interesting visualization in the project, and it's a visualization of something called diffusion tensor imaging. And what that measures is the direction of flow of electrical activity in the brain, and you can use that to trace out pathways, which are represented by these lines. The colors tell you the direction of the flow, whether it's front to back, side to side, or up and down. And then we've traced with little particles the flow of information through the brain. Thank you. Next slide. So let's talk a little bit about this distinction. We saw some things, well, some of these videos were created, rendered out. That's a process that can take a very long time. But some of them were, while they were playing them back as rendered movies, they're actually created in the real-time computer graphics system. The latter has a lot of advantages. It allows you to change parameters. It allows you to look at a simulation but fly around it at the same time. You're not stuck with one point of view or one way of looking at things. But of course, there are disadvantages as well. It's harder to deal with bigger data sets or do more complex things. When we want to talk about the idea of having a scientist use the dome for data exploration, the more we can do with real-time computer graphics, the better. That way we can really explore rather than just watch. So typically we present information in the planetarium, but it's also a place where we could explore it. And what needs to happen is really if we can expand what we can do in the real-time system, that just frees us up to do a lot more. And the capabilities that are coming, thanks to computer gaming and this incredible generation of graphics cards, allows us to load in bigger and bigger data sets and do more and more complex operations. And so I mentioned to you this idea of programmable graphics shaders, and this is actually how we've been doing a lot of our recent planetarium work. And what that means is that this represents the graphic pipeline, but each one of these parts of that pipeline that are in green can be accessed through computer code. And this is a really powerful opportunity for planetariums. So there are a number of different real-time planetarium systems, and they all allow us to do a number of very interesting things. But a lot of times when people want to do something custom or unique that that system doesn't do, that's when they have to go and make a movie. But by accessing the shaders, what we can do is actually, in the real-time system, build that capability. And more, actually almost all of the major planetarium vendors let you access the graphic shaders in various ways. It's often not well documented and you have to talk to people, but you can often do that in almost all the major systems. So let me go to the next slide. And it's really one area that I think there's opportunity that's being missed by the planetarium field for not doing more of this. In fact, our most recent production, Planet 9, which talks about the reasons why scientists believe there might be a large distant planet in the solar system. Much of that was done. This is a shot that was done with time lapse. But the vast majority, probably 70% of the show, was actually rendered from a real-time system, but it was rendered using custom graphics generated by graphic shaders that we produce. So there's an example. That's actually Mike Brown pointing at the poster there. So if we go to the next slide. Here's an example of that. So because of the power of some of these modern cards, you can actually deal with pretty large data. In fact, this is a shot. I'm going to show you a clip in a little bit. And actually, we can bring this down and play the Planet 9 clip. But this is the simulation that really led to the Planet 9 hypothesis. And so for a long time, people had seen some peculiarities in the structure of objects in the outer solar system. But really the theoretical basis for why that might be was a little bit uncertain. And this provided that basis. So in this simulation, we're looking at the solar system, and then we're hypothesizing a large planet with a purple orbit. We're now populating that with thousands, I think 4,000 Kuiper belt objects whose orbits go far out in the solar system. And we're going to play time forward 4 billion years and see what happens. So this is a large simulation over a large period of time. We're able actually to load that entirely into the graphics card, and we're able to control how we draw these orbits by writing our own graphic shaders that look at the system time and solve Kepler's equations and do things like that. What happens in this simulation is you see the effect of Planet 9 is to clear out objects in the outer solar system. Many of them are completely ejected. But over time, what happens is that objects that are aligned opposite of the alignment of Planet 9 actually have stable orbits. And that's what we see in the real observational data. We see 7 or 8 objects that go quite far out with orbits all aligned in the same direction. So actually, we don't, if you want to, okay. Next slide, please. So here's another example of creating sort of custom visualization work inside a planetarium system using programmable graphic shaders. In this case, in both cases, we were using UniView, which does a nice job of exposing those shaders to us. And in this case, this is actually a simulation run by one of my colleagues at the Adler Planetarium. And what you're going to see is something we created actually for a scientific conference that was at the American Museum of Natural History. And I was talking with Aaron, and he was telling me about his presentation. And I said, hey man, if you're going to go to a planetarium, you shouldn't give your talk on a regular PowerPoint. You should really ask and see if they'll let you use the planetarium. So I'll show you what we created for that. So if you can bring down the slides and play the M45. We just flew away from the Earth, and we're headed towards the Pleiades. And this is the age of the Pleiades, currently about 100 million years. And what we did is we replaced the observed stars with the simulated stars. And the thing is, we've now been able to run time backwards. And as we run time forwards, you see the effect of gravity. You also see stars evolving. So the most massive stars evolve, become supergiants, and they explode. We have little icons representing some of the end products of that stellar evolution. So the little swirly green things are black holes. The little purple spinny things are neutron stars. And later on, you'll see some triangles to represent white dwarfs. None have formed yet. You see we've blown up the stars so that we can see their different types. We've actually put a shader. These are billboards like we saw before, but we wrote a shader to show limb darkening in the star according to the best knowledge about how that happens. Now if we pull out, what you'll see is that in the course when these stars, which are often in multiple systems, have that supernova, they get tremendous kicks that will eject them clear out of the galaxy. And so we're actually tracing those paths. It's actually kind of terrifying if you think about it. These star clusters are producing black holes that are flying around at high velocity. We'd never see it coming. And now as we zoom in again, we're going to show how that cluster is actually being pulled apart. It's being pulled apart by the tides from our galaxy. It's stretched over these 100 million years. If we were to come back in a billion years, there would be no Pleiades, right? It's actually a really rich data set. And one of the reasons why it's great to do it in real-time graphics is just to fly around and explore. So here's one thing that we found just by exploring. This is an interaction between 8 stars. So you see the binary systems flickering on and off. And we're going to see a couple of these stars get together and actually right here and eject this red star out of the cluster through this multi-body interaction. So the shaders can be run in multiple passes. We can render the star, we can render the trails, we can turn that on and off, and here we're actually fading away the trails as we get further away. But we have complete freedom in how we want to draw stuff. So that's one of the reasons why I think this is such a rich avenue for the planetarians to explore. The vendors have been using it to create all the effects that we see in our software, but we can do it too. So we can do things like this. I just transitioned between the 3D view and this 2D diagrammatic view of the HR diagram. And in the software, I can actually run a slider back and forth and transition between the graph view and the 3D view. So you see the most massive stars make black holes. The next most massive make neutron stars. You see the neutron star cooling. You see the complicated stellar evolution paths. So this is a topic that I'm going to close on, is this idea of showing this kind of two-dimensional information in a planetarium. That we're finally getting a white dwarf there. All right, that was a little silly. I apologize. Yes, those star collisions are really rare, and we're not pointing any out in this visualization. But I think there might be one or two that occur. Yeah. So this is a little more diffuse than a globular cluster. What we also see, what's also being simulated is the mass exchange between binary pairs. So things like blue stragglers and all of that. So for the very last thing I'd like to talk about has to do with the sort of extension of looking at that HR diagram in context of the 3D simulation. And also one of the tools that we're going to need if we really want to fulfill that promise we talked about with inviting researchers into the dome. And that has to do with this split that actually exists in the planetarium community between what's called InfoVis and scientific visualization. In fact, if you go to the big visualization conference, they actually have two different parts. They have three different parts, but one is InfoVis and one is the visualization conference. And they have their conference in the same place, but they have different sessions and different people go to the different parts. They're very different communities. In the InfoVis world, which is InfoVis is things like graphs and pie charts and line charts. You're seeing a couple more sophisticated examples here, but it's a lot of that traditional scatter plots that people do in science. And it's something that typically in a planetarium show we would avoid. We would try not to show information that way. But I've been thinking about ways to use the dome and to mix this sort of two-dimensional information visualization with 3D information. And if you saw some of some of the graphics I showed from Planet 9 that had sort of an InfoVis kind of aesthetic. So if we go to the next slide. So you may have heard that we have a new president in the United States. And for some of us, that was a little concerning. And in particular, that got me thinking a lot about the need to educate the public around certain scientific topics. So for much of this year, I've been working on creating content related to climate change. And a lot of that content, a lot of the information that we want to present is really traditional plots and graphs. It's things like the temperature warming over time or carbon dioxide concentrations. And so the question was, how can we show that in a dome, but in a way that makes use of the dome, in a way that makes use of some of the unique characteristics of the dome? And so we actually created a presentation that we showed on Earth Day. There was a large march for science in Chicago. We had 200,000 people who marched from downtown to where the museum campus, where the Adler Planetarium is located, to speak out for science being represented in our decision making, our national decision making. So I'm going to show you, this is actually a little bit of an extended piece, but I'll close with that and show you how we're exploring different techniques of doing this two-dimensional information visualization in the planetarium. So if we can bring this down and play that last movie. So our Earth is the only place in the solar system where we know that life exists. And we saw the habitable zone there in green. And we're going to sort of zoom into the Earth. And I'm going to head to a spot in the Philippines where we will talk about the sun. So, life on Earth is incredibly diverse. Some incredible number of species. All those species are supported by the energy we get from the sun. And we can think about that interaction. So, energy comes in the form of light from the sun. Some of that gets reflected, about 37%, off of clouds or ice or whatever. The rest gets absorbed and it warms the Earth. And that warm Earth radiates light back out into space as well, but it radiates in longer infrared radiation. So this balance between the energy coming in and the energy going out is what we call our energy budget. And the great thing is we're actually constantly monitoring that. So this is one of the lessons we were trying to make in the show, is that, you know, we aren't just making this stuff up. So this map here shows the amount of radiation, the shortwave light from the sun that gets reflected and off and we don't absorb. And this map shows the amount of energy that we're radiating away in the infrared. So we have satellites constantly monitoring the Earth. We know what comes in and what goes out. And this balance between what comes in and what comes out is what sets our temperature. When they're in balance, the temperature stays the same. When they fall out of balance, the temperature changes. So I'm headed into the atmosphere. And the vast majority of our atmosphere is made up of nitrogen and oxygen, 80% nitrogen, 20% oxygen. And it turns out that this gas is completely transparent to the energy, the light, infrared light that our Earth emits. It just goes straight off into space. It doesn't care about any of this gas. But there are other trace gases that matter. And in particular, carbon dioxide, which you saw there reflecting that infrared radiation, because it's got 3 molecules instead of 2, it's able to interact with this light. And that's the key difference. So even though it's only a trace component of our atmosphere, it plays this huge outside role in maintaining our temperature. And that's important because without carbon dioxide, the Earth would be very cold. We actually need the greenhouse effect. The problem is that we're changing the composition of these gases. So we're flying now over Mauna Loa. And it was here at an atmospheric observatory back in the 1950s where an environmental scientist named Charles David Keeling started measuring the concentrations of CO2 in our atmosphere. We'll actually start looking at that plot going back to the 70s where we started to get really good data. And we'll see like when you measure over the course of a few years, you see a seasonal variation. And this has to do with the fact that in the summer, plants grow and they absorb carbon dioxide out of the atmosphere. And in the winter, they decay and they release that carbon dioxide back in the atmosphere. But when you start measuring over longer times, you start to see this general increase as well. Now, from a visualization point of view, what you're seeing here is we're using this graph. We're actually creating the dynamic scaling to make this point about how the carbon dioxide levels are going up and up and up, and it's a little bit terrifying. And we just set a new record last month, and we're over 410 parts per million. Best estimates are that we really need to be below 350 to prevent some of the really adverse effects of climate change. But by putting things in their geographic context, by creating this dynamic scaling, we begin to sort of increase our ability to create stories through the visualization. I bet that's a time warning, right? We're almost done, sort of. So now we're looking at this plot of the temperature over time. So this is the global temperature anomaly. And what we've done is we've plotted in blue years that are a little cooler than the average, and in red years that are hotter than average. And we're also tinting the Earth the same color based on the average global temperature. And of course, what we've seen is that in recent decades, that warming has been pretty intense. And in fact, last year, 2016, was actually by quite a bit the hottest year on record since we have this really solid climate record going back to the 1880s. It's kind of fun to put time in this context as well and watch the sun, watch the retrograde motion of the planets. Now, we have some other estimates of or sort of proxies that help us get at climate going back even further. So I'm going to plot myself down in Japan. And let's see if we can find, there's Mount Fuji. And it turns out that by looking at when cherry blossoms bloom, we have an estimate of the average March temperature in Kyoto. And that's been recorded all the way back to more than 1,000 years. So you see here, we're really trying to make the point that there's a lot of data, and we use the fact that we have a lot of dome space to show how much data is there. I've actually never seen this in the planetarium before, so. So here's a plot. Of course, it turns out that if we look at different countries, the amount of carbon dioxide per person that everyone's emitting varies by incredible amounts. And in the United States, you see that we've been one of the worst emitters. This plot actually shows the relationship between how rich a country is and how much carbon dioxide each person emits. So what you saw was that early on there was this linear relationship. But it doesn't necessarily mean that when you get richer, you have to emit more carbon dioxide. So if you look at the path that China's taken and the path that, say, France is taking, you see very, very different results. So there are ways that we can both be wealthy, but without destroying our environment. And really what path we take determines our future. And certainly in the United States, we've made a lot of progress in the last decade. And the part of the message that we were trying to tell is that we wanted to keep making that progress and not turn backwards. Anyway, that's the end of my presentation. Thank you very much.
Muchas gracias, Mark. Muy bien, ahora después de esta presentación, todas las utilidades y funcionalidades que vimos en todas estas herramientas que nos ha presentado Mark, pasamos a un espacio de preguntas y respuestas. Mark tiene un aparato de traducción para quien guste hacerles preguntas. Julien, ¿dónde estás?
Okay, thank you, Mark. It's really amazing all the data we can visualize on the dome. Of course, well, you mentioned, for example, that most of these works are available through Digistar 6, but well, I believe that really few planetariums here in Mexico have Digistar 6. We're probably the only one so far. What option exists? Are these images or videos available on the Data2Dome sites or for other vendors? I'm a Digitarium user, for example. I don't think that it would have the capability to render this kind of thing in real time. So what are the options to access this kind of visualizations?
Thank you. Well, of course, the capabilities vary across different systems. But I think in most cases, most of what I showed could be done in most systems. I think the one thing, because it's very new, that you really needed Digistar 6 for was that Data2Dome automated discovery service. But if you go to my website, actually no, if you go to, well, I have a GitHub site for the International Planetarium Society Science and Data Visualization Task Force, and I have some examples of how you could build your own Data2Dome service. So you can, for instance, search for things and download them and copy them into the files you need. So there are ways, the answer of course depends on what system you have and what you're trying to do. But I think there are ways to do everything I saw in almost every system. Sometimes it's easier, but.
Thank you very much for this wonderful talk. As an astronomer working here at the Politecnico, I find it really amazing all the things you can do with these visualization tools. And I was wondering, for the Pleiades simulation, well, you just said that in general, you do the simulation like you do a regular simulation in any astronomical issue, and then someone takes it and makes the visualization. For the Pleiades simulation, first you do let's say we have the Pleiades, and then you traced the orbits and the evolutionary paths of each star, and then you visualize it, and then you say, let's put, let's say, the red giant star, we will make it big and red, so you can visualize it. So that's the work of the visualization team, or is it part of the simulation? I mean, does the people doing the simulation have to give you all these details, or is the person in charge of the visualization doing that?
Yeah, so in this case it was pretty tightly coupled, because we actually ran that particular simulation for the point of doing the visualization. But what actually went into that? So it turns out you can actually do a lot in the visualization engine. I could write my own n-body system, for example. But this was a little bit more complex, because it included things like stellar evolution. It included mass transfer and binaries. It included the supernova kicks, right? So that was a pretty complex piece of code. We just had that code output the position, the temperature, the radius, the mass of the star at every particular time, and a star ID. So I could go in my real-time system. I actually made a little hack, and I used the time in the system, but I changed it so that 1 year equaled 1 million years. And then I went to time 0, like year 0, and made that 0, and year 100 was 100 million years. And then based on that information, we could decide where to draw things. It's smart enough because it knows that if I'm here at time A and I'm here at time B, I'll interpolate between those times and make for smooth motion. You're welcome.
Muchas gracias. ¿Alguien más? ¿Tengo un comentario? ¿Listo? Bueno, pues muchas gracias, Mark. Thank you very much.
De nada.
Le damos otro aplauso, por favor. Les pido nada más 5 minutos, no es necesario que salgan de la sala, nada más vamos a ajustar la siguiente presentación para continuar con nuestro programa. Gracias.